Hello! In my last video I showed you a fast sine cosine generator, but it had a backdraw that with a bigger step width the phase shift between sine and cosine was not any longer 90 degrees. How to extend the code that even with bigger step widths the phase shift between sine and cosine remains 90 degrees we will see after the intro. Today's video is an addition to the last video. If you haven't seen it, stop the video and look first the video 17EN. With the today's extension we will ensure that the phase shift between sine and cosine remains 90 degrees even with bigger step widths. As you can see, the output of the extended algorithm sine fast and cosine fast is nearly identical to the original sine and cosine function. Also, this extended algorithm needs no table and no floating point operations. Only an additional shift operation and addition is necessary. So we have for the extended algorithm in total 3 shift operation, 2 addition and 1 subtraction. First we will analyze the phase error from last algorithm and then come from the basic idea to solve the problem to the extended program code. Then I will compare the output of the new algorithm with the sine and cosine function and close the video with final remarks. With init cosine 120 and shift 2 we have 25 steps per cycle. So we have 360 degrees divided by 25 is 14.4 degrees per step, and we have a phase shift error of minus 7.3 degrees. This is roughly the half of the step width. With init cosine 124 and shift 3 we have 50 steps per cycle. 360 degrees divided by 50 is 7.2 degrees per step, and we have a phase error of minus 3.7 degrees, which is roughly the half of the step width. And in our last example we have an init cosine of 126 and a shift of 4, which result in 102 steps per cycle. 160 degrees divided by 102 is 3.5 degrees, and we have a phase shift error of minus 1.8 degrees, which is also roughly a half of the step width. Now to the basic idea. As we have seen, the cosine function is always delayed by the half of the step width. We cannot accelerate the cosine function, but with the existing data we can delay the sine function also by a half of the step width, and then the sine and cosine function match with a 90 degree phase shift. If the step width is not too big, we can roughly say the sine of the half step width is the mean value of the sine of the previous step and the sine of the actual step. Here our program code from the last video. To distinguish the sine from our last step and our sine from the actual step, we need 2 different variables. Before we do a calculation step, we store our actual value in the previous value. Sine old is sine new. Now we perform one step. Cosine is cosine minus factor times sine new. Sine new is sine new plus factor times cosine. And finally we calculate the mean value of sine old and sine new. Sine is sine old plus sine new divided by 2. Here our simulation spreadsheet. The formula from last time, the mean value calculation, the step width factor, and the related angle of 22.5 degrees. Here's the initial value of x. Here's the formula to calculate the follow-up values of x. Here's the initial value of y. Here's the formula to calculate the follow-up values of y. And here's a formula to calculate the mean value to shift the sine a half of a step width backward. And as you can see, even with a step width of 22.5 degree, we have a pretty fine circle, and the phase shift between sine and cosine is 90 degree. Now I change the step width factor 0.3, 1 divided by 4, 1 divided by 8, and 1 divided by 16. And you see, in all cases we have a very good circle, and the phase shift is always 90 degree. The code in C looks like this. Sine old is sine new, cosine is cosine minus sine new shifted to the right by shift, sine new is sine new plus cosine shifted to the right by shift, and sine is sine old plus sine new shifted to the right by 1. Like last time, I will put the source code into the video description. Due to the fact that the video description did not accept the lower and bigger signs, you have to adjust these two lines. The lower and bigger sign in these 4 lines. The shift signs in these 3 lines, and the shift signs in these 3 lines. Today I will only describe the changed source code of the main loop. The rest of the source code is described in the video 17EN. We have 4 signed 8-bit variables, one for the mean value of sine, one for the last value of sine, and one for the actual value of sine. And the cosine value will be initialized with init cosine. These 2 print lines should give us a little bit space to the previous output on the monitor, and here we have the main loop. First we store our actual sine value in sine old, calculate with these 2 lines one step, build the mean value of sine old and sine new and store it in sine, and finally we put the new calculated values of sine and cosine to the output function. The routine runs until the cosine value is init cosine and the sine new value is 0. After the main loop we do one additional step and stop the program with an endless loop. I will now start the program and execute it. And we can see now here in green our sine wave, and in orange our cosine wave. I will now change the main loop to an endless loop. And add some delay. And when I start it now, we see a continuous sine and co-function. I can now change the values of our generator. 126, shift 4 and offset -7, and restart the program. And now we have the continuous sine and cosine function with a sample rate of 102 steps. And now we compare the output of the extended fast sine and cosine generator with the real sine and cosine function. With init cosine 120 and shift 2 we have 25 steps per cycle and see a real good matching of the sine and the cosine function, and also we see no phase error. With init cosine 124 and shift 3 we have 50 steps per cycle, and the matching of sine and cosine is even better, and also no error on the phase. Here's the data for init cosine 126 and shift 4. Now we have 102 steps per cycle and also a good matching and no phase error. Finally, with init cosine 126 and shift 5 we have 212 steps per cycle. And like in the video 17En with shift factor 5 we have a degradation of the approximation, but the phase shift error is still low. We can summarize: with an additional shift and add operation we get a fast sine cosine generator with a fixed 90-degree phase shift between sine and cosine, even with bigger step widths. So we have an efficient solution for all applications where a 90-degree phase shift between sine and cosine is very important. For all other applications, the preferred algorithm is the one from video 17En. That's all for today. If you like my video, give me a thumbs up and subscribe my channel. And to be informed about new videos, activate the bell. See you in the next video. Bye bye.